Abhinav will take this lecture, and before that, I would like to introduce our camp, our initiative, and this organization. We are Inter-IIT Competitive Programming Conclave. We have united around 60 plus institutions in the country. About 10,000 plus students came together with us. I'm Ayush from IIT Madras, and my colleague Saitya Misra, Gauris Palig, and several other team members are here to invite you with the camp, which is about to end in like 10 days. So we have around four more lectures in advanced camp left and on the last lecture in the novice camp. So nothing would be possible without our two sponsors. One is Algozenith, which is a premium platform for internship, placement, preparation, comprehensive programs, DSA development, and several other stuffs. Students from lot of colleges, different colleges and uncircular branches have secured top positions at IITs, at top positions at different companies like Google and all. We had Vivek Gupta sir taking the first session, and first session on dynamic programming, and he is also the co-founder of Algozenith, which was a very nice session. You should, watch that lecture if you are starting the camp now. Our second sponsor, by that is 0xPPL. It was founded by Prasanna Shankar. He was earlier the founder of Rippling, a very nice guy. A 0xPPL basically empowers the next generation in crypto and Web3. We all know how important Web3 is. So, and it has hired several ICPC World finalists. You can join 0xPPL if you are excited about opportunities in startups, and he would be more than happy if you connect to him with Prasanna at the rate 0xppl.com. So now today we'll be having session on lazy propagation. It will be Abhinav who will be taking this session, and Abhinav is an amazing guy from IIT Madras, my senior here, and very nice person. He is master on Codeforces and currently doing an intern on in Sprinkler. So I hope you all would enjoy the lecture, and we can continue with the lecture. I think Abhinav.
All right. Hello, everyone. I'm Abhinav. Hopefully, you can hear me. Let me just share my screen. Okay. I hope everyone can see the slides. Drop a comment if you can't. And I see none, so I'm going to start. Okay. So, in this session, I'm going to start with a very quick recap on how segment trees work. We'll then go into the basic ideas behind lazy propagation, how to implement lazy propagation, and then some example problems. And then, depending on how much time we have left, I'll also be touching on segment tree walks, which are a very cool technique that's basically binary search on a segment tree. Okay, so getting into it, let's start with a quick recap of segment trees. I'm not going to go into details, but this will be helpful to think about lazy segment trees. And in particular, we're going to do this recap by thinking of functions. The reason for this is, again, it helps when you come to lazy trees. So, a segment tree represents an array of n elements, and you have two functions that you can apply on this array. So you have one function that combines two values in the array and gives you another value, and you have another function which updates a value. So in short, you have this combiner function f of x, right? Which could be something like find the sum of two values, find the product of multiple values, find the min of values. And this is what I'll call f. A very important property here is that it's associative. So if I'm trying to find f of an array, it doesn't matter in what order I take the individual f's. And this is what lets a segment tree work, because when you're querying f of the array, we split it into two subarrays, and then we split each of those into two subarrays, and so on. And the second one is the updater function, like I mentioned. So this applies some operation onto a value and gives us a new value. So I could have an operation like add k to this position, subtract k from this position, set at this position, multiply, anything. So in a segment tree problem, we always have a problem that uses these two functions. And one type of query is update using the updater function g. And another type of query is find the sum using the combiner function f on some range. And that's basically what segment trees let us do. I'll give some quick examples. So let's say you have a segment tree where you need to find the maximum of a range and you need to add to a certain position. These are what your two functions will look like. The combiner is just the maximum of xy, and the updater just sums up x, which is the value, plus k, which is the updating value. And now let's say we want a GCD on a range, and we want to set the value at a position. The combiner is just the GCD, and the updater, this is important, the updater just returns k, which is the update value, which makes sense because we're trying to set that position's value to k, so we don't actually care about its old value, which was x. Now, in both of these cases, the combining function is pretty simple. In fact, it's just a built-in function. So you might be wondering why we had to go out of the way to describe a whole new thing for this. There are multiple problems in which the combiner is not so trivial. So I've attached a link in the slides. You can check this out later. I'm not going to go into it in the lecture, but yeah, sometimes the whole point of the problem is just to figure out what the combiner is and what the updaters are. Okay, moving on. Yeah, so the problem I've linked is Savage in brackets. It's a very classic example of a segment tree with a non-trivial combiner. Basically, you need to find the maximum length of a regular bracket sequence in a string of brackets. Yeah, and now these are what segment trees do. So you have a query operation on your segment tree, which finds the value of f, that's our combiner function, on a particular range of the array from L to R. And one important thing that lets us do this in O of log n time is that we can do this only as much as necessary. If we arrive at an intermediate node whose range, so every node represents a range, and if the range represented by that node lies completely within this L to R of the query, then we just return the value of that node. We don't go any further into its subtree. And that's actually the key trick to making query work in log n time. And on the other hand, we have the update operation, which changes the value of A at some position using our updating function G. And this operation goes all the way to the leaf that contains that particular position in the array, but it still takes only log n time because we're only traversing to a single leaf. And a single part in a segment tree can only be at most log n long. So now, if we wanted to make range updates, there is one thing that we can change to this update function that would make it work in log n time, similarly to a query. And that's basically the only difference between the query and the update here. The query only traverses as much as necessary, while the update is traversing all the way that's required. If we change the update function to traverse as much as necessary, similar to the query function, then we basically get lazy propagation. And that's because traversing only as much as necessary and not more than that is just being lazy. That's where the name comes from. So this is the basic idea behind lazy propagation. And now let's go into the actual details. So a quick overview of what we're going to do. We're going to have to change the update function. And we'll also have to do a couple of things that are not done in a normal secretary, which are pushing updates, combining updates, and we'll also have to implement those into the build modify functions and everything. I'll run through this with a full example of how this works, so don't worry. So the main problem in lazy propagation, when I say the problem, it's like the problem that you would apply lazy propagation to. You want to support fast range updates. So you have an array A, and you want within some range LR, you want to set all of the elements to their value after you apply this updating function with some parameter k. And you need to do this in log n time. That's the main trick. You can't just go to every leaf and do it because that will take over some time. So, like I mentioned earlier, instead of going all the way to each leaf that we need, we'll borrow an idea from how we did the range queries. And so, we'll only go as far as we need down the tree. We're not going to go more than that. So, now, let's think about why this worked for queries. When we had a range query, why were we able to only traverse as much as we need? And that's because we stole the values of these queries. We stole intermediate values, basically. We didn't store values only at the leaves. We stole values at every intermediate node, so that when we come to an intermediate node, and if we know all the leaves within that subtree are going to be added to the result, we already have the result of all the subtrees at that node. And this is the main thing that we need to do for lazy operations. We need to find a way to store these operations as well in subtrees and in intermediate nodes, and not just in the leaves. So to do this, let's start by introducing a new array. So normally when you build a segment tree, you have one array, which is T, or you can call it whatever, it stores the value at each node. We'll introduce a new array called lazy, which stores a lazy operation value at each node, which is basically a range operation that's pending and has to be pushed down. So here's a very small example. You have a 2-element array, and we're doing a range sum on this with range set updates. And as you can see, initially we start with all the lazies initialized to null. So no lazy updates are pending. We have 3 and 1 in the array, and the sum is 4. That's in the root. So let's start. First query is to update L equals 0, R equals 1 with K equals 2. So basically let's update the whole array. And since we have set updates, we're basically going to set both of the elements in the array to 2. Now we start at the root, and since we know that the root already covers the whole array, we're not going to push down anymore, because as we mentioned, we're only going as far as we need. So we simply update the lazy value of the root to 2, indicating that we have an update operation that all the leaves of the root subtree have to be updated to 2. And we leave that. So that seems fine. But now we come to the next query, which is query the whole range from 0 to 1, which is again query the whole array. So now question number 1 is, how do we calculate the intermediate value of this node if it has an intermediate lazy operation as well? I'll come to how to solve these challenges, but first I'm going to show you what the challenges are. Now, there's also another challenge which comes up later. Let's say I want to update only the first element and I set it to tree. Now I traverse down the whole tree. I need to, because only that leaf will mark only the first element. And I set its lazy value to tree, which indicates that I want to set that value to tree. Now if I query the first element, which is again only that particular leaf, we need to account for two things. First, we need to calculate the value of this leaf, given the fact that it also has a lazy operation pending, which is doable because we know how to do this for leaves. It's just a simple update as a normal segment. But now we have another issue. There is a lazy operation here on the parent. And if we simply say, since this is a range set update, if we say that there is a lazy value of 3, and I'm going to set this to 3, that doesn't account for the fact that there was a lazy operation up here, saying that all the leaves here have to be set to 2. So we run into issues when we have lazy operations on both a child and its parents. And that's a particular issue. Let's get into how to solve both of these. So to solve the first issue, we need to have an update function which can work even on intermediate nodes and not just on leaves. So here's what a normal update function would look like. And maybe in your code, you just write P of v equals set value. And this works because on a leaf, the subtree is just a leaf. When we're writing this for a single node, we have to use other properties of the node. In particular, most of the time, you're going to have to use the length of a node. Or for example, here the root represents the range from 0 to 1. So the length of the root is 2, which indicates that basically 2 elements of the original array are present here. And you need to do that obviously. So for example, here you have range sum and range set. So if I give you a node and I say it has, let's say, k leaves in its subtree, and I'm going to set all of their values to x, what does the value of this node become? And the value of this node is the sum of all the elements in its subtree. And the way you get that is very simple. You just get the value that you set it to into the length of that node. That will be the sum of this particular intermediate node. And you can see that this works for leaves by default because a leaf has a length of 1 since it represents only one element in the array. And for all intermediate elements, it's equivalent to saying let's set all its children to 2 and then take the sum. So this is our new update function. We need a function that takes a vertex in the segment tree and some update parameter k, and then gives us the value that we would have if all of the leaves in its subtree were updated to g using that parameter k. This is kind of formal, you can skip this definition. Because when you actually code it up, it's pretty simple. It just looks like this. So here you can see the update has for vertex v and range L to R, and we're updating with k. For our range sum and range set, it's very simple. It just returns k into the length, which is R minus L plus 1. And for different types of queries, it's very easy to modify this. Let's say you had a range maximum query, then the range maximum is only relevant to one element. So it actually doesn't change with the length. So if you have range maximum queries and range addition updates, then this update function will just add whatever you're adding in your update to the currently stored maximum. I'll get to more examples. So the second challenge, as we saw, if you have lazy operations that are already pending on the parent node, you don't really know in what order to do these operations or which takes precedence. But if there are no lazy updates on the parents, then it's very easy. We just apply the lazy operation on the current vertex because we know that there are no clashes with its parents. And obviously, we don't care about lazy updates on its children either. They don't modify, they don't affect this particular. So let's try pulling off a slightly scammy trick. What if we can ensure that whenever we visit a node, there are never lazy updates on its parents? And the way you do this is something like induction. When you start at the root, since it's the root, it has no parents. So there are no lazy operations on the parents. And then when we move to one of its children, we need to make sure that there are no lazy operations on the root. How do we do that? We're basically going to push the operation down. Because a single node represents a segment of the original array, but this same segment is also represented by both of the node's children. So if I wanted to add k to some segment of an array, I can either add k to the segment 3 node, which represents that segment, or I can add k to both of the children of that particular node. And this is the main trick which allows us to do pushes. Basically, whenever we move from a parent to a child, we're going to push any lazy operations that are stored at that parent down to both of its children. And this will not affect anything. So for example, here we have two segments, both are basically the same. And I'm trying to say I'm going to do a set operation on the whole array. So range 0, 1, and k is 3. So this gets represented as a lazy operation on the root across the whole array with 3. And now let's say, for some reason I'm traversing down to the first leaf, which is the node with value 3. Then I want to make sure that the root doesn't have a lazy operation. And to do that, I can do a push like this. So the lazy value from the parent goes down to the children. But there's still an issue here, if you notice. I said it was range sum and range set. So now that we've set both of the leaves to value 3, the sum that is being represented on the root node should be 6. It should not be 4, because both of these children have a lazy value of 3, which means they'll be set to 3, and the sum of 3 plus 3 is 6. But we got 4. So that's one issue. So I'm going to come to how to solve that. Okay. So this is very simple. We need to find a way of finding the value of these children after we apply this lazy operation, and then combine those values using our combiner function. But finding the value of a child after applying a lazy operation is something that we just solved. I mean, we solved for any vertex, find the value after applying a lazy operation. And we can just use that. So this is what a push function looks like. We set the lazy values of the children to the lazy value of the current vertex, and then combine both of their updated values, which is the value after applying the lazy, and then resetting the lazy operations at node v. But again, there's still one more issue here. And the issue is here. When we say that the lazy of the children is simply equal to the lazy of the current vertex. This is wrong because suppose the children already had a lazy value of 1. Then you can't just override the lazy values. I mean, in this particular case, you can because you're setting values. But if it was a range addition modification, then you can't just overwrite values like this. So we need a way of combining these lazy operations themselves. Using the code. I think that's not possible, but I will get to an implementation part with better code for everything later. Okay, so we need a function to combine operations. We'll define a new function for this. Let's call it h. And to avoid confusions with the value combination function f, we're going to call this the composition function so that it composes operations x and y, and we'll denote it by h. So some quick examples. For range add, let's say I want to add a value x to all the children of a particular node. And now I also want to add value y to all the children of the particular node. What's the final value added to all the children of that node? It'll just be x plus y. So this is a very simple composer function. And for range set updates, if I want to set all the children of a particular node to x, and then a later update comes and says I want to set all of the children to y, what do I output? I output y. And here it's important to note that the order of operations actually matters when you're doing these set operations. Okay. Now I'll give you a very big example of just operation. So here we have a segment tree. The underlying array is 3147, has length 4. We're going to do range maximum queries and range addition updates. So you can see here that every particular node is the maximum of its children, and we initialize with all the lazy values as 0. So first let's start by figuring out what the combine function, the update function, and the compose functions. So quick reminder, the combine function combines two values, which are the numbers inside the nodes. The update function tells you how to combine a value, which is the number inside the node, with an operation, which is the number outside the node. And compose tells you how to mix together two operations, which are the numbers outside the nodes. So let's get into it. For this particular case, the combine function is just the maximum, which makes sense because we're looking at range maximum queries. The update function, since we're doing range addition updates, is just adding k to the currently stored value. And this works because if you have the current maximum in a range, and then you add k to all numbers in the range, the maximum element is still the same, and its value was only increased by k. So we just return the currently stored value plus k. And the compose function, so if we need to combine two range addition updates together, we just sum them up. Very simple. Okay. So now I'll go to an example of actually running this particular segment tree manually on these queries. If it gets slow or boring, tell me. I can stop halfway if you get the idea. Anyway, let's start with query 1.3. Since it's 0 indexed, 1.3 means this whole part, which is 147, and we should return 7. So normal segment tree starts at the root, but 1.3 is not stored in the root, so we go down. Now this 2 and 3, but this tool does not store only 1. So this particular node goes down 1. And now these two segments represent the entire segment that we are looking for, which is 1 to 3. And we can take the maximum of these two for the value, which is 7. So yeah, recap of segments. The first one is done. Now we want to make a range update, 0 and 1. So that's the first and second elements. And we're going to add 2 to both of them. So once again, start at the root. 0 and 1 is contained entirely in the left child. So we'll move only to the left child. And now since 0 and 1 is entirely within this node, we just set its lazy value to 2. But we're not done yet. We need to update all the parents of this particular node to make sure that our path is maintained. So we go back up, and now we update this. When we update this node, we have to use the total values of these two nodes. So this node still has value 7. This node now has value 3 plus 2, which is 5. But a maximum of 5 and 7 is still 7, so this node doesn't change. Right. Now we're going to add 5 to the whole array, which is 0, 3. Very simple. Start at the root. The root stores the whole array, so we just add 5 to its lazy. And that's basically the solution. The next one is to query 0, 2. which is the first to the third element. And as you can see, the original array is here. We should be getting a value of 10 from this. Anyway, let's start. Start at the root as always. Now the root doesn't have this, so we need to traverse down to its children. But before we do that, since we have a lazy operation here, we have to push the lazy operation down. So that's the first step we do. We've pushed, I'll move back one step so that you can see that again. So this lazy operation of 5 moves down. So this particular node, which had a lazy operation value of 2, has now become 2 plus 5, which is 7. And this one, which had no lazy operation, now has a lazy operation of 5. And we've updated the parent node to the updated values of both of these nodes. Now you have 7 plus 5, which is 12 on this side, and 3 plus 7, which is 10 on this side. The maximum of 10 and 12 is 12. So this node becomes 12. Now we can traverse down to the children. 0, 2. Okay. I think I forgot to traverse here. Right. So you traverse down here. And 0, 2. Okay, we're going to query here. And I think I made a mistake. It should be querying on this side as well. But hopefully you can see how it works. Since it's completely contained in this array, you just take the updated value and return that, which is 10. Because you get 3 plus 7 is 10. You don't need to go down to the leaves because this stores don't need it. And you would have gone down this side as well, but that would only give you 9. Okay. Now we have update 1110, which is just update the second element to add 10. Again, very simple. Start at the root, go to the left child, and now we need to go to the right child. But before we go to the right child, we have to push the lazy value down. So once again, we push 7 down and then update this value to the maximum of 3 plus 7 and 1 plus 7, which is 10. And now we move down. We've reached the particular node that we need to update. We add a lazy updater, which is 10. So its initial lazy value was 17, was 7, now it's 17. And now we need to move upwards and update everything again. So we go one step up to its parent. Now its parent should take a value which is a maximum of 10 and 18. So it should take 18. And now we go up again. And this node should take the maximum of 18 and 7 plus 5, which is 12. But the maximum will be 18. So it will stay at 18. And finally, we have query of the whole, which is just maximum on the whole array. Look at the root is 18. The answer is 18. Okay. Any questions here? This is basically how a lazy segment tree works with pushing and stalling lazy updates. Okay. Assuming no questions. So now let's look at how to actually implement this. So I'll go over all the main changes you have to make from a normal segment tree and how to actually set everything up, all the variables and functions you'll need, and then we'll go through it in detail. So the main changes are, you will have noticed during the example, the first thing is that whenever we want to get the value of a node, we don't just take T of V, we have to apply any lazy operations which are at that node, and then take the total value after that. The second change is that whenever we go from a node to any of its children, we have to push operations down. So any operation that is on the current vertex has to be pushed down to both of its children. And when we make that push, we combine the lazy operation of the node with the lazy operation of the children, then update the node's value, and then set its lazy to 0. So just step-by-step pushing, if it was still confusing. Once again, combine lazy operations of the children, then reset the lazy operations at the node, because the whole point is not to have any lazy operations pending on the parents, and then update the value of the node using these updated values of the children. And when we say values, as from the first point, we need to apply all the lazy operations at them and then get the value. We don't compare just the values. Okay, so here are some variables that you'll want when you're actually writing a lazy segment tree. First of all, let's start with two basic data types. So you'll have one for storing the values of each node and one for storing the lazy operations. So we'll call these val and op. Most of the time you can get away with just using int for both, but sometimes we'll do different. We'll get into that. And now we'll have a vector t, which stores the values at all node. And we'll have a vector of operations, which is just lazy of, which stores the pending lazy operations at every node. Next, we'll have our combining function, which combines two values to give us another value. This is what we call f. We'll have an apply function, which takes all the lazy operations that are pending at a particular node, applies them, and gives us a final value. This is basically what we previously saw as the updating function g. We'll have a compose function that takes two operations and puts them together to get a new operation. This is what we call h, our composition function. And finally, we need a function to actually push any lazy operations at v down to its children. We'll call this just push. And then we have your typical build function, query function, update function. These are kind of the same things that you'll have in a normal segment. Okay. So, going to this in detail. First, the first step of any lazy segment tree problem is actually choosing your data types for the values and the operations. So the values, obviously, you need to have information to answer queries. So if the problem is asking for range maximum, you need to store maximum. But sometimes you might want to store extra information that makes it easier to actually combine two nodes together. This doesn't appear in easier problems, but for example, the problem I linked before with the advanced combiner function that takes two operations and puts them together to get a new operation. This is actually very easy to do because you just need to have two operations and you just need to have okay. Hello. Can you hear me? There was a power cut here, so I'm not sure. Oh, okay, good. I'll restart. Where did I cut off? Right, I'll just redo the whole thing. Okay. So value could have extra information that's not needed to actually answer the query, but is needed to combine two values together. For example, as I mentioned in brief, there was that problem where you have to find the length of the longest regular bracket string. So at every node, you store the length of the longest bracket string. And basically the trick is to also store the length of the longest number of closing brackets, the number of closing brackets and the number of opening brackets. And then you could do something like when you're combining it, it's either the maximum of the longest regular bracket string in either of the two segments, or you can combine all the opening brackets from the first segment with all the closing brackets from the second segment. Yes. Just to give you an idea of how that works. Okay. And onto the second data type, which is operation. You need to find something to represent the operation. So normally if you have something like set all values to x or add x to all values, it's very simple. You just need x, which is an integer. And now both val and op need to have an identity element. This is kind of important for the implementation part. So the val identity is something such that the combine function always returns x if you try to combine x with the val identity. And it's similar for the op identity, except for the op identity, it's compose. So compose op identity with x will always return x. And there's also one more thing, which is if you apply the identity operation to any value, you will always get that value out. So basically, if the lazy value at a node is the operation identity, then we know that we actually have no lazy updates pending. So just a note about actually choosing these identities. They're not always mathematical identities. For example, if you have addition, an identity element is 0 because any element added with 0 is itself. And for multiplication, an identity element is 1 because any element multiplied by 1 is itself. But let's say, for example, you have set operations. So this is an operation that takes x and y and returns only y. You can't really have an identity for this because there is no single number such that if you set any number to this number, it will always be the initial number. That's not possible. But since we're not doing maths, we're doing programming, we can make a workaround like this. We choose some element that will never actually appear in the array. So most problems that have positive AI, you can just choose -1. And for other problems, you can choose something that's very high or very low, like -10 to the power 18 or 10 to the power 18. And then we just make a quick check. In our apply function, we check if it's equal to this particular element, just return x. And similarly for a compose function as well. If anything is equal to the identity, just return, always return the other element. Okay. Now we go into the combining function. The combining function is very simple. We just need to combine two values. So we don't really need to care about lazy operations at all. And these are just examples of the mathematical functions from before in programming. So if you have range sum, you just have to add the two values together. For range min, you just take the min of the two queries. And note that for the range min, I've taken the identity to be 10 to the power 18. Because for a normal problem, if AI was less than 10 power 9, then the minimum of any element in the array with 10 power 18 will always be that element itself. Okay. The composition function is similarly simple because here you don't need to care about the actual values. You only need to combine the lazy operations together. So for range addition updates, as we mentioned before, just add the values together. For range set updates, we have an old operation and a new operation. Most of the time, we're going to return new operation. But there's one catch here. If the new operation is itself the operation identity, then we need to return the old operation because that's basically telling us we're not doing anything in the new operation and maintain the old operation. Okay. If identity, yes, you can do that as well. I think that's called lazy tagging. Some people use that in their implementations. That's possible. You can store a boolean that just tells you if you need to make a lazy update or not. Okay. Now we come to the slightly trickier functions. So you have the apply function where you need to actually take into account both the value of the node and the lazy operations at the node. So one of the simplest apply functions you can have is this. If you have a range maximum query and a range addition update, then T of V represents the maximum in the subtree and lazy of V represents the value to be added. So we can just return T of V plus lazy V. But let's say now we have range sum queries and range set updates. Since we have range sum, the sum of a range is going to be modified by the length of the range as well. So here we have to take into account the length of the range. And I've also added a catch to just make sure if the lazy identity is there, return the original value. Otherwise, let's say we set all the values in the range to some x, then we want to return that x into r minus l plus 1, which is the length of the range from L to R. There is a small mistake here. I'll actually ignore this T of V. Since it's range set, you should only have lazy V. Okay. Now the pushing function. I'll go through it step by step. It's not that hard, but it has multiple things going on. So the reason we have L and R in the arguments is because we are going to need to call apply later on. There's no other reason. Push itself doesn't actually need L and R. So if you want to push from a node V, we have to set the lazy values of both of its children. So this is what this step does. And you'll notice we don't just set, we make use of our compose function to combine two lazy operations into a new lazy operation. The next step is to remove all lazy operations from the current vertex V. So we can just set lazy V equals operation identity. And then we have to combine the values of the children to get the new value of this node. And you'll notice that in the combine function, we have to use apply. We can't just put t of 2v and t of 2v plus 1 like we do in a normal set tree. But otherwise, it's pretty straightforward. This is the whole push function. Not too hard. Now update function. So quick clarification. Update here, v is at node v. L and R is the range L to R represented by node v. Capital L and capital R is the range in which we're trying to put our update, and K is the update parameter. So let's go to this one by one. First of all, if our current range, which is small l to small r, if it's outside big L to big R, we don't need to do anything. We just return. And now if L and R is fully inside big L, big R, then we also don't want to propagate anymore. So we still have to return here. And what we'll do is just add the lazy value of our current operation to whatever lazy value is already at the node. We do this using the compose function. And then we return because we don't want to propagate any further since it's lazy. Now we come to the third case. This is a trickier case. So let's say the range small l to small r intersects with big L to big R, but isn't completely inside it. Then we might need to push to the left child, we might need to push to the right child of v. So let's calculate v, let's calculate l, let's calculate r. You'll notice that calculating mid and then doing both of these, this is similar to a normal set tree. In fact, everything here is very similar to a normal set tree. You just push update down to the left child, which is 2 into v, right child is 2 into v plus 1. The range of your left child is L to mid, range of the right child is mid plus 1 to r. And you want to change the range of the update itself from capital L to minimum of the mid and r, and maximum of L and mid plus 1 to r, just to make sure that the ranges stay close. This whole part is very similar to a normal set tree, except for one part. Notice that we have to push all operations down before we go to the children. That's important, otherwise, as we mentioned, you can have conflicting values. And finally, as in the push function, we just need to update the value here at this node. So we call combine function, and the values we need are the values we get from applying all lazy operations on the children to themselves. So this is the entire update function. This is what it looks like. Pretty simple. You notice that this is actually very similar to the query function in a normal set tree, which also has a case like this to exit early if your current range is within the query range, or otherwise go to children. Yeah. The difference from an update function in normal set tree is basically in the fact that we use apply and the fact that we have to push the children. Those are the two main tricks that I mentioned always happen for the lazy set tree. And a particular unique trick to the update function is to never propagate more than needed. If we're currently fully inside the range, just return. Okay, query function. This finds the value of some range, L to R. This is pretty similar to a normal set tree. The only difference here is that you have to push before you go to the children. Very simple. So you notice here, we call apply to get the value of a current node instead of just saying t of v. And here, before we go to querying the children, we push all values at v to its children. That's not a lot of differences. So just look at it once. Finally, the build function. This is what you call when you're starting the segment tree. So you'll set the recursive function where you start from the root and then go down to the leaves and then set the values of the original array and come back up and combine all the values as you go. In fact, you don't need to change this at all because you only call it in the beginning, and in the beginning there are no lazy operations. So it's just the same as a normal segment tree. And when you're doing it, just make sure that you initialize the array t to be val identity. All elements should be the identity value, and all elements of lazy should be the operation identity, op identity. Or if you're using a Boolean to mark whether the vertex has a lazy operation or not, you can just set that to entirely false. Okay, so that was implementation. I'll share the slides later if you want to use the code. I can maybe share my template as well. But let's get into problem solving with lazy segment trees. So if you want to solve a problem with a lazy seg tree, you need to break the problem down and figure out a couple of things, which are very much related to the concepts that we had in implementation. You need to figure out what information to store at each node, which is the value. How do you actually represent an operation, and what are the operations the question is asking for? How do you combine the value at two nodes, which is the combine function? What is your apply function? How do you apply an operation to a node? How do you actually combine operations together, which is the compose function? And how do you push lazy operations to the children, the push function? This is all you need to figure out. And once you figure these out, you're free to start coding and solve the problem. It's also worth noting that most of the time the push function is actually the same. It's just compose the lazy to the children and then reset the lazy. But sometimes it changes because the left child might get a different lazy value than the right child. I have an example in which that happens, so we'll get to that. So let's go to some quick example. So this is the question prefix some queries on CSS. I've shortened the question here. You have an array A and you have two kinds of queries. You need to update A k, so at some position k, to be a new value u. So this is point setting. And you also need to find a maximum prefix sum in the range A to B. Okay, A is not array, it's A to B as in constraints, but yeah. So how could you solve this with a lazy segment tree? Okay, you're going to skip to the answer. So the idea is to use the prefix sum array itself. Since the queries that we get are relating to the prefix sums, let's just use prefix sums all the time. So now if we're building a prefix sum array, updating the value of an element is equivalent to just adding a value to a suffix of the prefix sum array. Because you update that element, and all the prefix sums starting from that element will be changed by the change in value of that element. So now if we have a lazy segment tree, query 1 is just add a value to a range, and query 2 is find the maximum in a range. Because the maximum prefix sum is the maximum element in a prefix sum array. And then we just have to subtract the prefix sum of A minus 1, which is just some casework. Okay. Just to give a quick recap, let's look at what each of these particular functions and variables are for this question. So we know that we need to have a range addition update and a range maximum query. So both of our value and operation will just be integers. Now our combine function, again, range maximum query, so we'll need maximum. Our apply function, we have range maximum and range addition. If you add a number to a particular segment of an array, the maximum just increases by that value. So we just have to add the two values together. And our compose function, if we want to add two different numbers to a segment of an array, it's equivalent to adding their sum to the whole array. So we just have to sum the two operations together. And that's it. This is one question done. Okay. So now the next question. This is a bit trickier, so I will give you some time to think. It's a simple task. That's its name. It's from Codeforces. And the question is, you have a string S, which contains lowercase English letters, and you have two types of queries. Query 1 is take all the letters from I to J and sort them in increasing order. You don't have to output anything, but this does change the current string. Query 2 is do the same, but you sort them in decreasing order. And you just have to print the final string, which is after all of these operations. So how will you do this? Try putting thoughts in the comments. Yeah, that works. I will wait for 5 minutes. The trick to this question is really figuring out how we are going to use a lazy segment tree, because it's not immediately obvious. Install 1 for increasing, minus 1 for decreasing. Okay. How exactly do you do that? Okay, wait, I get your idea, but there's an issue. These operations can affect each other. So if I have a string and I solved one particular subarray, and then I solved another subarray which intersects with the original subarray, I need to know in what order I sorted both of these. How do you handle that? Okay, I'll give you a quick hint to speed things up. Notice the fact that there are only lowercase English letters. So you only have 26 letters. So instead of actually salting, you can just use counting salt, which is count the occurrences of A, count the occurrences of B, and then just put that many A's, that many B's, that many C's. Yeah, it'll take time to think of this. This is, I think, 2300 weighted or something. It's not simple. But once you get the idea, it's kind of obvious to see how to get a lazy segment tree. That's how most questions are actually. The lazy segment tree is not the most complicated part. The complicated part is figuring out how we are going to use the lazy segment tree. So quick overview of counting salt. You just need to count the occurrences of each letter inside some range, and you also need to be able to set its occurrences. So you need to count. There are, let's say, 5 A's in this particular range, and then I want to say this particular range, which is of length 5, I want to set it with all A's. And that is how we'll make our sort. Good. I mean, check the actual rating, I don't know. But yeah. And now counting the occurrences and setting occurrences, that sounds like what we've done. So to count the occurrences, we can do a range sum. To set the occurrences, we can do a range set. And we have 1 if the letter is present and 0 if the letter is not present. Note that the trick is we're using a different lazy segment tree for every single letter. So we have one lazy segment tree for the occurrences of A, one for the occurrences of B, one for the occurrences of C, and so on. It sounds bad, but it's not. Yeah. Oh, the next example has left and right nodes taking different values. So now that you know what to do here, again, quick overview of what val, op, combine, apply, compose are. You need to do range set and range sum. So for both of these, value and operation is just int. Combine, we're doing range sum. So we have to take a sum. Apply, range set. So we just return the lazy value. Unless the lazy value is the operation identity, in which case return the current value. And compose is the same thing. Same thing we saw before. Basically, always take the newer operation unless it's the identity. If it's the identity, take the older operation. And now once you do this on every single, once you do this on every, so now if I want to solve range I to j, first get the count of all letters within I to j, and then I to I plus count of a, set it to a, I plus count of a to I plus count of b will be b, and so on. You can see the editorial, it's pretty well. Okay. Last example, this is a very tricky one. I don't have a link, but it's a very classic problem. You have sum array A, and you have two types of queries. One is give me the sum of all elements from I to j. And the second query is to add an arithmetic progression to range ij. The first element is x, and the common difference is k. So basically, I add x to the element at position I add x plus k to I plus 1. I add x plus 2k to I plus 2, and so on until I reach j. Again, I'll give you 5 minutes. Think about how you can represent this on a lazy segment too. Pre-computation. Okay, I'm interested to hear that approach later. But X and K can vary with different queries, and it's online. Okay, storing the first element and the common difference is correct. Okay, how do you do the pushing? Right, I'll go to the answer. That's basically the correct idea. Yep, correct. Perfect. Nice. So the way we do this on a lazy segmentary, the value at a node is just going to be an integer, which is just a sum. But an operation is now going to be a pair. The first element of the pair represents the first term of the AP, which is x, and the second element will represent a common difference k. Now, if we want to combine two values together, we just have to add them together since we have range sum. To apply, we need to actually add the sum of the AP. So you have T of V, which is the current sum, and lazy V dot first is the AP's first term. So the first term will be added to every single element, so we just multiply it by the length of that range. And the second term, we do your standard AP sum formula, which is range into range minus 1 by 2 into common difference. This is our apply function. Okay. And this is what our compose function is going to look like. Again, it's simple. If you're adding two arithmetic progressions to a range, they're both independent. They don't actually interfere with each other. So you can simply add up both terms separately. And the pushing function is where we get different here. Because when you actually push the operation down, the left child only gets the first term of the AP and a common difference. But for the right child, the first term is not the first term of V. It's the first term plus the common difference into the length of the left child. And the common difference will be the same. We can push that down. But yes, that's it. This is the trickier one, I guess. So if you start understanding how to work with different kind of combining functions, apply functions, compose, push, you can pretty much solve any segmentary question. Okay, last part works. I think you can take attendance now. I will finish off soon. Okay, that works. Okay, so segment 3 works. I thought that the first part would take much longer, so I made this part short, but I think we have enough time to take it properly in detail. So a segment tree walk is basically binary searching using a segment tree. For example, let's say we have a problem where you have to make an update which is set all elements in a range, and you have queries which will find the first element which is greater than some value x. Now, one approach to do this is to simply make a segment tree that supports range set updates and range max queries. And then you can perform your typical binary search with L, R, and in every iteration, check if the maximum from 0 to mid, so the prefix maximum, is greater than k using the segment tree. And how fast will that be? The binary search will take log n steps, and the segment tree itself takes log n steps for each query. So you'll actually end up with log squared n steps, which is usually fine because log n is usually very small. But there are some questions in which log n squared is not fast enough and you want to have log n. So to actually get a log n binary search using a segment tree, you need to realize that the structure of a segment tree is very similar to the structure of a binary search tree. Both are binary. And when you look at a segment tree, the root represents the entire array, and it has a left and a right child representing the left and the right half. And every node can be split into its two children, which have left and right halves. So instead of binary searching and then querying the value using a seg tree, you can actually directly walk on the segment tree from the root. So by what I mean by walk, when you have a normal binary search, you start with the feasible range being the whole array. And then you query the midpoint, and you decide if the feasible range is the first half of the array or the second half of the array. And you keep doing that and halving the feasible range. If you want to do that on a segment tree, you start at the root because the root represents the whole array, and you choose whether to go to the left or the right child. Choosing either one of these will halve your feasible region. And then from every single vertex, you can choose to go to the left or the right child, and you keep halving the feasible region, which is basically binary search. But since you're doing this whole thing while going down the segment tree, you're actually only using log n steps in total, because the length of any path from the root to a leaf in a segment tree is just log n. So just to formalize this, when I say first true, I mean we're going to look for the first value, for the first position at which some function evaluates to true. So we have some monotonic function which is like false, 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 true, 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 true on some array A that we are representing with a segment tree. So we start at the root. That means we're looking at the whole array. Now, if the left child satisfies the condition, go to the left child. Why does this work? Because let's say the left child is storing like the prefix value of that condition that we're checking. So if the left child is true, that means there is some element in the left child which satisfies the condition that we're looking for. And if the left child satisfies the condition, then obviously any element in the right child cannot be the first element, because we know there's an element in the left child. So we can basically throw away all of the right side children and go straight to the left. If the left child doesn't satisfy the condition, then we look at the right child. If the right child satisfies the condition, then we can throw away all of the left side children, because we know they are definitely not the first, and go to the right. And if both the children don't satisfy this condition, then we just return -1. That indicates there is no index that satisfies the condition we're looking for. Okay. Hang on, I see something in the comments. Start at node if its max is greater than x. Yes, exactly the same thing I just explained. Left always takes priority and you just move to the children. Correct. And we also just have to handle the special case if we're on a leaf, then there are no children. And if our current node satisfies the condition, we just return our current node. If the current node doesn't satisfy the condition, again, just say there's no result. So this is how you'd implement it on a lazy segment tree, going over it line by line. We need V, which is the vertex. L and R is the segment represented by the vertex. And we have a function that returns a Boolean value based on the value stored at this vertex. That's our checking function. And this has to be monotonic in the array. So here's how we start. We know that when we walk, we intend to go down to the children. And the first rule of implementing a lazy segment tree is whenever you want to go down to the children, always push first. So we make a push. And then we check if we're on a leaf node. So that's what the check L equals R does. If we're on a leaf node, check if the value at this node satisfies the condition. If yes, simply return this position, otherwise return none. For the check function, we use apply instead of just taking the value t of v because we need to account for any lazy operations here. Otherwise, it's not a leaf. We need to look at the children. So let's look at the middle element, calculate the middle element. And now first check the left child. If check of the left child is true, then walk to the left child. Ignore the underscore. That's because I copied it from my implementation, which has some slight differences. And walk to the left child is just 2 into v L mid, same checking function. And if the left child doesn't satisfy it, check if the right child. If the right child satisfies, then walk down to the right child. But if both children don't satisfy it, just return -1. This is a very simple walking function. And this is for a lazy segment tree. If you want to implement this onto a normal segment tree, it's pretty much the same. Just remove the push function because on a normal segment tree, push does nothing. And then whenever we have apply, so here, oops, okay, here, and here, you need to change apply blah 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 to just t of 2v, t of 2v -1, t of v, because the value of a node is just whatever is told there. That'll give you a walking function and a normal seg tree also. There's nothing specific to lazy here. Okay, I'll close. This is the last part of this lecture. Again, a slightly difficult question, but so this is the question minimum array from Codeforces. And the shortened version is you have an array A. You have operations which tell you add k to every element from I to j. So range addition updates. And you're just going to store all of the arrays after each operation. So you have A, 0, which is before any operations, A1 after the first operation, A2 after the second operation, A3 after the third operation, and so on. And the goal of the question is to find the lexicographically minimum array among all of these AI. And lexicographically minimum means that if A is lexicographically less than B, then A and B share a common prefix. It could be like an empty prefix. And the first element of A after the common prefix is less than the first element of B after the common prefix. So it's like you compare by the first element, then by the second element, and by the third element. And as soon as at any position you get that A is less than B, you report A less than B. If A is equal to B, you keep going to the next. Okay. So think about how you would solve this question. I'll give a few minutes for thinking. Also, you can fill out the attendance form, I guess. Okay, I'll give you a hint for the people thinking about this. When you have a normal array and you want to find the minimum element in this array, you normally go to all the elements in order and keep a track of the current minimum. And if your element that you're considering is less than the current minimum, you update the current minimum to be that element and then continue onwards. See if you can use that in all the arrays here. Okay, I see an idea. We can use walk to find the first position. Well, AI greater than AJ. Yes, that's very close. That is the right idea. You want to use a walk? Okay, I'll give you the solution. But there's one change that you need to use a walk to find the first position. Well, AI, let's say you're comparing AI and AI plus 1. So you've only applied one operation in between. You need to find the first position. Well, AI is not equal to AI plus 1. It's not necessarily that AI is greater than AI plus 1. It might be that AI is less than AI plus 1 as well. If you can find the first position where it's not equal, then you just check if this position is, lower or greater. If the position is that AI plus 1 is less, then AI plus 1 is the new minimum. But if it's greater, then we can just skip AI plus 1 and go to the next operation. And I'll cover how to rebuild a tree also. That's kind of rare, but there's a scam trick to that. So here's the idea. We'll go to all the operations in order. We'll store the index of the previous lexicographic minimum array, and we'll only store the differences of each element from the previous minimum array. So initially, for example, the previous minimum array is just the first array. And if we start with only the first array, then the differences are all zeros. And then once we apply the first operation, we will just add k within that range on this array of all zeros. Now, at any point after adding some operations, we need to check if it's lexicographically less than the previous minimum. How do you check that? If the first negative element occurs before the first positive element. Think about why that's true. A negative element, since we're storing the differences, a negative element would indicate that at that position, the current number is less than the number in that position in the lexicographic minimum array. And a positive element would indicate the number at that position is greater than the number at that position in the lexicographic minimum array. And since we know that an array is lesser than another array lexicographically, only if the first non-common element is lesser than the element in the other array, we need a first negative position to appear before the first positive position. Because if the first non-equal position is positive, then our current array is just greater than the lexicographic minimum. So to do this, we're going to need to store two kinds of information in our lazy segment tree. We're going to store range maximums. We're also going to store range minimums. And we'll also have two kinds of operations, updating operations. We'll have range addition, which is the query that the question asks us for. We'll also have range set. This is related to rebuilding the tree. So at any point, to apply an operation, we just do the range addition. And then we can find the first position that's negative and the first position that's positive by doing a sec3 walk. The walk will have to be independent for each. For finding the negative position, we basically find the first position such that the prefix minimum is less than 0. To find a positive position, find the first position such that prefix maximum is greater than 0. You can find both of these in log using a walk. Then just compare these positions. If negative appears before a positive, we have a minimum. If positive appears before negative or negative is not present at all, then we can just go to the next operation. Supposing the current array is minimum, then we say that this is the new lexicographic minimum. And since we're storing the differences from the lexicographic minimum, we now have to make all the elements 0. So this is the part I think that you mentioned as rebuilding the tree. But here it's very simple because again, it's a segment tree. And range set is always a possibility. So set all elements to 0 is just range set to 0. And now in the end, we know the index of the lexicographic minimum array. So we can just use a normal segment tree or a normal lazy segment tree to add up all the operations until that point and output the final array. That's how you would solve this problem. Okay, that's it for my slides. This was faster than I expected. Any other questions? I can just get quickly into the implementation of that, but if you want to have range addition and range set, you would need to have your operation as a pair of integer, similar to the AP. And here the first element will be what you need to add, and the second element will be what you need to set. And the compose function will also be different, because for the compose function, if you have an operation which you set elements, that will always overwrite any additions. So if your new operation has some set value, then we need to, in the output operation, we set the addition to 0. Whereas if you're just adding something into new operation, we don't really care. Hang on, what do you mean by precedence? Okay, precedence between setting and addition. Yeah, that's what I mentioned. I think, give me a second, I can try opening my submission for that. Yeah. Do you want to see the code or? Cool. Anyone else have any questions? Cool, that's nice. You can try implementing your own segment tree template using the base functions I've put here. Just make sure to have using value and whatever type you're putting at the top. That should be fine. All right, I think we're done then. Sec trees advance into sec tree beats, yes. But honestly, as you saw with the so-called simple task, when it comes to segment tree problems, the hard part is usually identifying that you need to use a sec tree and how you're going to use the sec tree. It's not actually implementing the segment tree, because a lot of hard problems are usually just your typical range addition, range set, range some kind of lazy sec tree. But actually getting to the point that you realize you need to use that sec tree is the tricky part. Sec tree beats is pretty advanced. You won't need that right now, I think. Yeah, if you want practice problems for lazy segment trees, you can always check CP algorithms has, CP algorithms will have a list of problems at the end. There's also the ultimate topic list by you know who. You can just Google that. It's literally you know who ultimate topic list. And there, if you go to the lazy segment tree section, you'll have a collection of problems to practice. And a lot of problems with lazy segment trees will be very high weighted, but don't let that deter you. Once you realize it's a lazy segment tree problem, just figure out all these functions like I mentioned here, and then you'll be able to implement it. Okay, then I think we're done. Thank you, guys.